Hello, my name is Martin, and in this short video we'll learn a little bit more about cyclic voltammetry, or CV for short, and try to understand why a CV looks the way it does. If you're interested in more details about how to actually perform measurements, or if you want to know something about the subtle differences between a true cyclic voltammetry and a staircase voltammogram, then you need to look for the videos on experimental design. So, when we're measuring cyclic voltammetry, we apply a potential to the working electrode that is changing linearly with time, from a starting position to a switch point and then back again. And during this time, we're continuously monitoring the current that is flowing through the working electrode. Here is a cyclic voltammogram of ferrocene methanol on a glassy carbon electrode. As we can see, we have two distinct regions. One where the current is increasing as we scan the potential, and then as we move over the peak, the current decreases despite an increased driving potential. To understand this, we need to have a brief look at the theory governing electron transfer from a molecule to the electrode surface. The deeper quantum mechanical theory behind this is known as the Marcus-Husch theory, and it's quite complicated. But luckily, in many cases, the simpler phenomenological Butler-Volmer equation works quite well. Here, we see that the main part is an exponential dependence on the potential for the forward reaction and another one for the reverse reaction. This works similarly to the Arrhenius equation, with the equilibrium potential being a kind of activation energy and the applied potential providing the driving force. The current is also dependent on the concentration of our reactant and a pre-exponential factor that depends on the particular reaction we're looking at. We also have the number of electrons and the Faraday constant. From this, we should expect the current to increase exponentially with the potential. We can check this by plotting the current on a logarithmic scale. We can then see that at least initially we have an exponential increase of the current. But as we move up the peak, the curve starts deviating from an exponential and eventually even starts going down. The reason that the current increase slows down and eventually even starts decreasing is that we're running out of molecules close to the electrode to oxidize. As we're applying a higher and higher potential, the exponential nature of the Butler-Volmer equation makes sure that the driving force very quickly becomes very, very big. This means that any molecule that touches the electrode is instantly oxidized. As more and more molecules are oxidized, we see a depletion layer growing close to the electrode. That is, a layer that is depleted of molecules that can participate in the electrode reaction. As time goes on, this layer grows thicker. That means that molecules need to be transported from further and further away. The transport, if we're not stirring our liquid, happens by diffusion. This is the random jiggling of molecules in the solution. Diffusion is relatively slow on large distances, meaning that it takes time to replace the molecules at the electrode surface. Another way to put it is that as the depletion layer grows thicker, the gradient of concentration becomes smaller. According to Fick's first law, the flux of molecules is proportional to the gradient. We now understand that the concentration in the Butler-Volmer equation is the concentration at the electrode surface. So if we want to calculate the shape of a cyclic voltammogram, we have to solve the Butler-Volmer equation with C given by the diffusion equation. Unfortunately, in general, this combination is not solvable analytically. We can do it with computers, and we regularly do computer simulations, but we cannot write down a simple equation that gives the shape of a cyclic voltammogram. One thing that we can solve is the simplified case at very high overpotential. At that point, as we mentioned before, any molecule that comes to the surface is instantly oxidized, and the concentration at the surface is zero. So the current is then independent of the potential and completely controlled by diffusion. The solution to the one-dimensional diffusion equation is known as the Cottrell equation, and is one of the best known results in electrochemistry. The Cottrell equation relates the current with the diffusion coefficient for the molecule in question, but there is no specifics about the reaction itself. The current is decaying over time as T becomes large, I asymptotically approaches zero. We can make a quick experiment to test if this is true. Here is the current measured over several minutes in ferrocene dimethanol at a potential of 0.5 volts, a few hundred millivolts above the redox potential. If we try to fit the data to the Cottrell equation, we see that it doesn't fit very well at all. So what is going on here? The reason is that at short times we're measuring the charging of the electric double layer, and at long times even the slow convective motion that is almost impossible to completely eliminate is enough to stir up our growing diffusion layer. And Cottrell is only valid for pure diffusive transport. If we choose a smaller interval from a few seconds up to say 30 seconds, we get an excellent fit. This can be used, for example, for determining the diffusion coefficient of a molecule. So now we know the shape of the voltammogram before the peak. It's increasing exponentially, and after the peak the current goes down as 1 over the square root of T, and we can see how nicely we can fit it to the curve calculated from the Cottrell equation. But for a fast and reversible reaction, we can also calculate the current at the peak itself. The height of the peak depends on several factors. We have the diffusion coefficient, the concentration, the electrode area, and the scan rate. To understand why the scan rate matters, we need to think about that current is charge divided by time. And if we have a bunch of molecules and we want to oxidize them, and from each molecule we get 1 electron, and we oxidize them during a certain time t, then we get a certain current. Now, if we have the same bunch of molecules and we scan twice as fast, then the time is half and the current should be twice as high. But that's not what the Randall-Sevcik equation says. Remember that V equals E divided by T. The reason is that we don't have the same amount of molecules. During slow scanning, more molecules have time to diffuse to the surface during the scanning, and we saw in the Cottrell part that the depletion layer grows as the square root of time. These two effects taken together, think about that, results in a peak height being proportional to the square root of the scan rate, and this is valid for a freely diffusing molecule. A linear fit of the peak height versus the square root of the scan rate can give us either the diffusion coefficient or, for example, the real surface area. But beware that this only works with reversible reactions. For a molecule that's absorbed on the surface, the behavior is different. Since no more molecules are coming in by diffusion, a doubling of the scan rate actually leads to a doubling of the peak height. Looking at how the peak height changes with varying scan rate is an important way of distinguishing between diffusive processes and absorption processes. For molecules that both absorb and diffuse, the behavior can be more complicated. The same is true if we have electrodes that are porous, for example. So that's the end of this movie about cyclic voltammetry. I hope you've gotten at least some understanding about why a CV looks the way it does. So the wealth of information that can be extracted from a cyclic voltammogram is the reason why CV has become a favorite technique of electrochemists everywhere.